Hello, welcome to next session. In this session, we'll solve some conventional questions of compressible fluid. The topic is nozzle and diffuser. Question number one from Civil Services, Main 2009 is air enters a diffuser with a velocity of 250 meter per second and a temperature of 30 degrees Celsius. It leaves with a velocity of 90 meter per second. Neglecting friction and heat transfer, determine 1 exit temperature, 2 exit pressure if the inlet pressure is 125 kPa, 3 area ratio between the exit and entry. Will your answers change if there is friction present? Explain how. So first of all, calculating according to ideal flow, or we can say neglecting friction and heat transfer, and applying energy equation between inlet and outlet of the diffuser. So at inlet, the energy is V1 square by 2 plus CPT1, and at outlet, energy per unit mass is V2 square by 2 plus CPT2. We are assuming that there is no change in potential energy, and no heat is added, and there is no friction. Okay, so then the energy equation becomes like this per unit mass. So V1 is given as initial velocity, velocity at inlet is given as 250 meter per second, and temperature at the inlet is given as 30 plus 273, and Cp is your 1005, and V2 is your 90, and Cp is your 105, and T2 comes out as 330.06 Kelvin. Okay. So exit temperature is 330.06 Kelvin. So that can be solved by using energy equation. So when there is no friction and no heat transfer within the nozzle, so then the process is your reversible adiabatic process, or isentropic process. For isentropic process, we know that P2 by P1 is equal to T2 by T1 is for gamma divided by gamma minus 1. So here T2 is 330.06 and P1 is 03. So and P1 is 125. So P2 comes out as 168.69 kg. Okay. So this is your pressure. That is 168.69 kg. So now the third question is to find out area ratio. To find out area ratio, we'll find out the density at inlet and outlet by using state equation, that is P is equal to rho RT. So at inlet it will be P1 is equal to rho 1 into RT1. So P1 is 125 Newton per 3, and R is 287 and P1 is 303. So from this rho 1 is this quantity. So 125 Newton per 3 divided by 287 divided by 303. And rho 2 is just changing pressure, that is 168.69 Newton per 3, that we have calculated, and R is 287, and T2 is your 330.06. Yes. So this is your rho 2, and assuming continuity equation, so the mass flow rate for steady flow will remain same at inlet and exit. So M will be equal to rho 1 A1, V1 is equal to rho 2 A2 V2, and from this we have A2 by A1 as rho 1 V1 divided by rho 2 V2, where V1 and V2 are velocity. Okay, so rho 1 is this quantity 125 in cap 3 divided by 287 divided by 303, and rho 2 is this quantity 168.693 3 divided by 287 divided by 330.6. So and V1 is 250 and V2 is 90. V1 is 250 and V2 is 90. So area ratio comes out as 2.2465. Okay. So when so this is the area ratio when we are considering ideal process, isentropic process, as well as no heat addition between inlet and outlet. So when friction is present, the energy equation will remain same. Total energy, because we are not adding any heat, or so the energy equation will be satisfied. But energy equation is satisfied as well as continuity equation will satisfy, momentum equation will satisfy. But isentropic relations are not valid, so answer will change. This can remain same, but this will change and this will change. So answer will change. Conjugate ratio will change.